So I'm the director of the Stanford Intelligent Systems Laboratory. My graduate students call themselves Sizzlers, and we work on models and algorithms for intelligent decision-making under uncertainty. And here are a variety of different application areas, ranging from aircraft collision avoidance to driverless cars and drones and so forth. I'll drill in a bit today into aircraft collision avoidance because this represents a major opportunity for Julia, but I would say maybe a slight majority of my students are working on automated driving. So one of the major theoretical frameworks that we use in the lab is the Markov decision process, or an MDP. How many of you have used MDPs before? Okay, a small minority. So the idea of MDPs really ought to be taught in elementary school. The idea is really simple. You have a set of states. Here I'm showing 3 states, 1, 2, and 3. And the state just encodes what you need to know about the state of the world. So if you're trying to solve a driving problem, you need to capture the positions and velocities of the other vehicles on the road. Then depending on what state you're in, you have a set of actions available to you. So in this simple example, we just have 2 actions, A or B. And depending on what state you're in, what action you take, you end up in some new state according to some probability distribution. So if you start off in state 2 and take action A, you transition to state 1 with probability 0.6, or you just stay in state 2 with probability 0.4. So these actions might be turn left or turn right. The transition probability distributions might depend upon the behavior of the drivers and the dynamics of the vehicles. As you make transitions in the state space, you get rewards or penalties. So if you go from state 2, take action A, and then end up in state 1, you get a reward of 1. If you're in state 3, take action B, and transition to state 2, you get a penalty of 10. So this is a very general way to encode a sequential decision problem. The idea of Markov decision processes have been around for a very long time, since at least the 1950s with Richard Bellman. Solving these are a little bit tricky because sometimes you have to forego an immediate reward so that you can end up in some state downstream where you might be able to achieve a high reward. And in order to solve this, you can use something known as the Bellman equation, which is kind of like E equals mc squared and F equals ma. It's really simple, but it encodes intelligence. The most beautiful equation in my opinion. In fact, one year I incorporated the Bellman equation into my holiday card. My wife was like, "Why is there an equation between our kids?" So most of the emergent intelligence in the systems that we work on in my lab kind of falls out of the Bellman equation. There's a very nice generalization to the case where you don't know the current state. So instead, you observe the state indirectly. So you get these observations that are probabilistically related to your current state. And this is really nice because it captures things like occlusions, like in the context of driving, or maybe you have sensor limitations or sensor noise. It's just really great. And you can use something known as recursive Bayesian estimation to infer the probability distribution over the current state. And there are different ways to go about doing that. You could use just regular Bayes' rule, or you can use a particle filter or a Kalman filter, or any of these methods to determine the underlying state. But the objective is still the same. You still want to behave in a way that accumulates as much reward over time in expectation. So this is a very general framework. In fact, you can frame your life in terms of a POMDP, because you're uncertain about the current state of the world, you're uncertain about how your life will evolve, and you have very sparse rewards sometimes and random penalties that show up. You have to make your decisions wisely. So one of the challenges with both MDPs and POMDPs is that in order to solve real-world problems, you need a lot of states. In the context of aircraft collision avoidance, you need something like 8 quadrillion states, but unless you do a factorization, you can bring it down to about 40 million states. That's still a lot of states. And in the POMDP context, solving this exactly in the worst case, it's p-space hard. So it's really tough. It has scared away a lot of researchers in this area. But it turns out that for some problems, you can come up with good approximations. And in cases where there's a lot of structure to your problem, like in the case of aerospace and driving, you can arrive at good approximate solutions. There's another generalization to reinforcement learning. All reinforcement learning is just a Markov decision process, but you don't know the state transitions or the rewards ahead of time. You have to interact with the world to infer those distributions and learn how to behave. And fundamental to this is the trade-off between exploration of the world and building a good model and exploitation of that model to maximize your accumulation of reward. So I won't go into much more detail on this. So I'll just point you to a really great book that came out in 2015. It goes into MDPs, POMDPs, reinforcement learning, Bayesian networks, and so forth. And I teach a course every fall at Stanford on the topic. But I'll dive now into ACAS-X, something that I've been working on for the past 10 years. So ACAS-X is the next generation aircraft collision avoidance system. And it's currently being standardized for use on every large aircraft in the world. So interest in aircraft collision avoidance systems arose during the 1950s. There was this mid-air collision in 1956 over the Grand Canyon involving United Airlines and TWA. So as you can imagine, there was a press frenzy, congressional hearings, and ultimately this led to the establishment of the FAA in 1958. And with the establishment of the FAA, they put in place a number of procedures and introduced air traffic control as we know it today, and this significantly improved the safety of the airspace. But there were still these mid-air collisions, and these two happened over California. The one on the left is over San Diego. It was actually captured on film by a press photographer as it happened. So 144 fatalities. This made Congress realize that we really need an onboard system, a system that sits on board the aircraft that alerts pilots to potential collision. And so MIT, Lincoln Laboratory, and MITRE Corporation, so I used to work for Lincoln Laboratory, they were tasked with developing the system known as TCAS, or the Traffic Alert and Collision Avoidance System. And that's currently mandated worldwide. But it wasn't actually mandated in the United States until after this Cerritos collision in 1986, just a few miles from Disneyland. So TCAS works like this. It has a surveillance system that detects and tracks intruders, and then it passes these sensor measurements onto the advisory logic. So the advisory logic tells the system exactly when to produce an alert and what alert to provide to the pilots, and what guidance in terms of the vertical rate to direct the pilots. This gets passed on as a resolution advisory to the display. So there was a ton of effort that went into building the advisory logic, and it has evolved over the course of a few decades. Any guesses as to how many pages of code is required to create a robust system like this? So I presented this to the computer science faculty at one of their lunches, and they took a look at the slide and they counted up 3. It's not 3. Computer scientists have absolutely no appreciation for how challenging aerospace problems are. And actually, my background is in computer science, and I really didn't, and I'm a 3rd-generation pilot, but still I didn't have much of appreciation for how tough this problem is. I thought, if an aircraft is above you, then just descend. If they're below you, just climb, right? So that works like 99% of the time. But the level of safety that we're aiming for is more on the order of fewer than 1 collision per billion flight hours. And in order to get to that order of magnitude, a lot's involved in order to ensure the robustness. So I'm going to show you a couple screenshots from this document that contains the TCAS specification. So this is RTCA DO 185B Volume 1, and it has 1,799 pages. So extremely complicated. But it has also been extremely successful. So ever since TCAS has been mandated in the United States, there has been exactly 0 collisions involving an aircraft carrying TCAS. So not all aircraft are required to carry TCAS. The small general aviation aircraft are not. So the planes that I used to fly when I had discretionary time. So the 1-seater, 2-seater aircraft, they don't carry TCAS. It's too expensive, and it's not really built for aircraft with those kinds of dynamics. But basically, any commercial aircraft is required to carry TCAS. The smaller aircraft that don't carry TCAS, they have collisions about every month. So this is obviously a POM-DP. And so the right way to solve this is as a POM-DP. And in order to do that, you apply dynamic programming. So we have 5 state variables. I'm zooming in on 2 of them, and we discretize that state space. This is how we get to the 40 million states. The vertical axis is our altitude relative to the intruder, and the horizontal axis is the time to closest approach. And so the intruder stays fixed relative to us. So the intruder is in that red square. I'm coloring it red because it's a really bad square. And good squares are green, and yellow is kind of in between. So I'm going to show you how dynamic programming works without showing you any equations. After the talk, if you haven't seen the Bellman equation, you should either find one of my holiday cards or look it up on Wikipedia. So I'm going to zoom in here, and the idea is really simple. I really hope you enjoy these videos because it took me and an animator at Lincoln Laboratory a long time to make these. So what we want to do is calculate the value of the state just right before that potential collision. And, so what we do is we use that probabilistic model, so that state transition model given a climb. So most of the time we end up in that kind of yellowish green square, but some of the time we end up in that top green square, and sometimes we end up in that red square. So what we do is we take a weighted average of those values. So we're mixing together paint colors, and then we tack on the cost of climbing, and that's the cost for climbing. We're going to do the same thing for not alerting, and it's a little bit worse, right? So climbing is probably preferable to not alerting in this case. And if we give a descend, then it ends up actually being a tie with climb, and to just break the tie, we go with descend. And we color that with the value of that action. We just repeat that process for all of the other states at that time step. Since you guys are really advanced, I'm going to skip forward just a little bit. And what you do is you just work your way backwards, just looking one step forward, taking a mixture of those values, and adding on the cost for that action. And the neat thing about this is it tells you exactly where you want to climb and where you want to descend and where you want to wait for a little bit. So this is great. So implicitly, this is just a cartoon, but implicitly it takes into account every possible trajectory through that state space. And that obviously grows with it grows exponentially with the time horizon. But it's able to do this computation on the order of about 7 minutes. And it takes into account not just all the possible trajectories, but their likelihood as well. So this is really the beauty of dynamic programming. So this is great. So we can encode much of the complexity of the collision avoidance system using this numeric table. But we still need to have some amount of code for things like the tracker for doing the table lookups and the interpolation and online costs and things like that. So we still need a representation of the logic that does the lookups. And this is encoded in the algorithm design description document, or ADD. So I was at Lincoln Laboratory. Lincoln Laboratory was tasked with creating the pseudocode and with much of the development. And Johns Hopkins Applied Physics Laboratory, or APL, they were in charge of developing the hardware prototype for the flight test, and they were working with Honeywell on this. So I used a pseudocode that I kind of made up that was roughly based on the Introduction to Algorithms textbook. And it resulted in having to spend a lot of time on the phone with this guy named Jeff Brush at APL. Lots of time on the phone, lots of long emails, really long emails, trying to disambiguate my pseudocode. I couldn't just say, hey Jeff, why don't you just execute it? Couldn't do that. And there wasn't a good way for me to test the code against my research C++ code. I needed to really make the code as fast as possible because I needed to run millions of these Monte Carlo simulations so that I could estimate the probability of collision as well as a set of other operational and performance metrics. So that was a really, really frustrating experience. And then some other people at Hopkins suggested using Julia. So this is December 13th, 2012. I went back and checked my emails, and they suggested Julia. This is before Julia 0.1, and I was like, what? Why would we use a language that doesn't even have a version number to encode a specification for a safety critical system? That just felt like a really terrible idea. And it was partially motivated by these folks at Hopkins that were in charge of leading the verification and validation effort of ACAS-X. So they were looking at using probabilistic model checking, formal methods, methods for ensuring code coverage of the specification. And they were attracted to Julia because it handles the abstract syntax trees really nicely, and it makes it easy for them to interface with their theorem provers and so forth. So then Julia version 0.1 came out in February. And then just to pacify the folks at APL, I decided to just code it up in Julia and run it against our research code. We also coded it up in Python. And we found that Julia was 50 times faster than Python. So we found it was 50 times faster than Python before Jeff Bezinson got his hands on it and made it even faster. So I thought that was kind of interesting. So I started considering it, and the idea of having a specification that we can use to give to the hardware manufacturers and so forth, but that we can also directly validate in fast-time Monte Carlo simulation, I thought that was pretty compelling. And so together with APL, we made the recommendation on August 5th, 2013, to use Julia for the specification for ACAS-X. That also happened to be the day of the first flight test of ACAS-X. And I would have to tell you that few things are more exciting than to be on a large aircraft, flying directly at another large aircraft, and hoping that this POMDP business works out. So the next month, Lincoln Lab hired Jeff Bezinson 1 day per week as a consultant. Then we transitioned the specification to Julia. So version 2 of the ADD was completely done in Julia September 30th, 2013. And then the next month, Julia 0.2 came out, and I moved to Stanford. So a number of features were added to Julia, such as a result of the ACAS-X effort. So like the workspace command, float16 support. So we use float16s for representing the lookup table. So code coverage, the Julia to C compiler via the LLVMC backend and so forth. This all came out of engaging the Julia developers as part of ACAS-X. So I'm going to run through a few interesting things here. So this is a screenshot of an earlier version of the ACAS-X specification. So you can see some explanatory text and then some Julia code here. There are references between the explanatory text and lines of the Julia code. It's a PDF document, so they're all hyperlinked. So just so that you can appreciate how awesome this is, the previous version of TCAS is a Word document, and all of this was done manually. Okay, this is all LaTeX. And it automatically figures out where different functions are referenced along with their page numbers. This is what the code looks like. We have inline comments that get translated to the explanatory text. So that gets translated to this. You can have the types associated with the code. And this part I think you'll like. It automatically figures out the code flow in the algorithm, and it actually auto-generates these graphs. So the inputs to the different functions and the outputs, and it shows how they all flow together. So the ACAS-X algorithms in Julia have been wrapped into this ASIM, the ACAS-X simulation interactive module. So the work on this started a while ago before we had a good Julia GUI interface. I think there's actually a talk later on GUIs and Julia. But at the time, the decision was made to do this in MATLAB. And so the manufacturers can directly interact with the code and validate their implementation. So generally, they have to do a translation to real-time C code. We've also developed other tools, actually a whole bunch of other tools. I'll just mention this one. This is available on our GitHub. This is joint work with NASA Ames. It's adaptive stress testing. So we originally created this concept for validating ACAS-X. It basically finds the most likely failure conditions given a probabilistic model of the environment and sensors and so forth. And it basically turns the problem into a reinforcement learning problem, of course. But this is completely general. We've also been using this for validating automated driving systems. So I'm going to discuss now a major effort within our lab, largely led by Zach Sundberg, who's here, one of my PhD students, on POMDPs.jl. So this is a really nice general framework for solving POMDPs. And it's really challenging to create a good framework for this. I'll outline some of the reasons. There are lots of really great frameworks for other kinds of machine learning, so like supervised learning and unsupervised learning. But in those contexts, you can specify problems. You can specify problems just through a data set. You have like your input data and then your labels, and it's just static, and you can give people that data, and they can try out different algorithms. But for POMDPs, there's this feedback loop, right? So your environment will generate some observations. You have to update your beliefs. Those beliefs get passed to the policy, and that produces an action, and that affects the environment. So you can't get away with just a static data set because it has to react to the things that your system is doing. So you need to specify that reaction using a program, and you might as well use the best programming language out there to do that. Best in terms of like readability, but it's also performant. We need these specifications to be fast because solving POMDPs is really involved, really computationally involved, and it often involves a lot of forward simulations. A major challenge is accommodating the wide variety of different solvers. So some solvers use things known as alpha vectors, others use searches through trees, like Monte Carlo tree search. Other solvers learn finite state controllers. Other solvers use deep reinforcement learning to generate these policies, like DeepMind did for Atari. There are also different kinds of interfaces. So for some problems, an explicit interface makes sense, where given your transition probabilities, you want to give an explicit representation of the distribution over the next state. And many solvers can take advantage of knowing that explicit distribution. But for other problems, you just want to have a generative model where you can encode a program that just samples the next state and gives you the reward. Because it's for some problems, you just want to sample a random number generator rather than producing a full probability distribution analytically. So there are different kinds of problems with discrete state spaces and action spaces and observations, but some are continuous, some are high dimensional, some are a mixture discrete and continuous. Some solvers are used offline, others are used online. Different kinds of belief representations, some with explicit probability distributions, some using particle representations. Others encode the current belief as a state in a finite state controller. There are different needs. As a faculty member, I want to balance between code that's easy, or a framework that's easy to use in my teaching and accessible to undergraduates and graduate students, but also fast enough to support cutting-edge research. So this is a snapshot of the interface. We want it to be easy to specify different kinds of problems. We also want to make it easy for people to write different solvers and contribute to the framework. We need to make it easy to run experiments. So we have a set of interfaces between those components. And Zach created this really nice gallery of a collection of different standard problems with animations that highlight the properties of different solvers, along with code to get people up and running. I would have to say that of all of the algorithms that I'm familiar with, the algorithms for solving POMDPs are some of the most conceptually difficult. And this is exactly where you want to have nice open source solvers that are available to everyone. So this resulted in a paper in the Journal of Machine Learning Research. It just barely came out, one of the first articles using a Julia package. So we created a Julia POMDPs organization. That's where you can find all of our solvers and problems and so forth. And what the keynote speaker yesterday mentioned, it's really important to me and my lab to make sure that all of our experiments are reproducible. And so the requirement for our papers is that they all be uploaded to GitHub, ideally with Jupyter notebooks. So I'm going to take you through a few of the packages that we've been developing in our lab. If you go to GitHub/Sizzle, you'll find a very long list, but I'll go over some highlights. So one is tixie pictures.jl. How many of you have used Tix? Oh, okay, good. I'm at the right conference. So, yeah, the manual for TICS is over 1,100 pages. Really, really great. Really great manual. Lots of examples. I read it to my kids sometimes. So it goes through it takes care of a number of annoying things like interfacing with Lua LaTeX and converting things to SVG. A number of other packages are built on top of this, like PGF plots. The plots produced by PGF plots just looks so beautiful. So the PGF plots, it's a LaTeX package as well. Really the only plotting package I would consider for publication quality venues. So it makes things really easy. You pass in a function handle and the domain to plot over, and it produces nice plots like this. There's also a backend for plots.jl for PGF plots. There's also TICS graphs. It does graph layout. All of the layout and typesetting is done by LaTeX, not any kind of imitation through MathJax or whatever. It's all legit LaTeX. This is not a Julia package. It's a LaTeX package that sits on top of Python Tech by Jeffrey Poor. So Python Tech also supports Julia. Really, really great package. The nice thing with this Julia plots package is you can specify different plotting packages to use. So if instead of PGF plots you want to use Gadfly, you just replace PGF plots with Gadfly, and it takes care of the embedding of the figure and so forth. So you can see the different outputs. If you go with PGF plots, Gadfly, or PyPlot, everything is taken care of for you. You can make up your mind about which one looks best. There's also basenets.jl. It's a Bayesian network package, so you can encode different kinds of conditional probability distributions, both discrete and continuous. It handles sampling. It also supports parameter learning, structure learning, and inference, and I use this in my classes. Like I mentioned, we do a lot of work with automated driving. So there's this automotive driving models, along with, I think, at least a dozen or so other driving packages. Packages for visualization and animation, driver models. So you can stick on different driver models and let them run, and you can collect statistics about their collision rate and so forth. We also have discretizers.jl that takes continuous data and discretizes it. We've implemented a variety of the standard algorithms out there. This is useful if you want to discretize your data to do structure learning, like with a Bayesian network, or if you want to visualize distributions. So I use Julia extensively in my teaching. All of my classes use Julia. So there's decision making under uncertainty. If you want to look at the course material, you can go to aa228.stanford.edu. My Julia notebooks are up there. So what I do in class is I use my Microsoft Surface Pro here, and I write my notes into OneNote, and then I can swipe over to Jupyter and run interactive notebooks with the Interact package, and students totally love it. And another class is multidisciplinary design optimization, and here's a plot of a Gaussian process. And it's really great. It allows the students to interact with rather complicated algorithms and build up intuitions. I also use it in an undergraduate course on building trust in autonomous systems. So I have them create their own aircraft collision avoidance system in 10 weeks. Never mind that it took us about 10 years. And as part of all of these courses, there's a competition. It motivates students. This is a leaderboard. You can visualize their the performance of different policies. This actually interfaces with OpenAI Gym in Python. But it creates this nice animated GIF so that students can see what's going on. I've also started using Vocarium, which is an online service. It supports interactive Julia notebooks, just like Julia Box, but it also supports auto grading and competitions and leaderboards and so forth. I also created, with the help of 3 high school teachers over the past few years, an optimization course for high school students. It's on GitHub. You can see both the presentations and Julia notebooks. But I'm going to end with this. This is a collection of a few pages from this new book that I'm working on called Algorithms for Optimization. This is with one of my PhD students, Tim Wheeler. It's all done in Julia. You can see the algorithms. We don't use pseudocode. We use actually executable Julia code. All of the plots are using PGF plots. It's inspired by Edward Tufte, so we have a lot of these small multiples, which is really useful for understanding optimization algorithms. So on the bottom left, you can see the simplex method as it evolves over time. Really, really beautiful. Actually, all of everything runs as a result of one run of Lua LaTeX. So it calls out to Julia. Every single image is generated on the fly. So much fun. If you're interested in looking at getting a preview copy of this book before I have to send it to MIT Press at the end of the calendar year, just email me. Here's my email address, and I'll give you a link to the book and the password for accessing it. And I'd love to have your feedback, and if I've missed any topics, you can let me know. But I'll stop here for questions.